Good afternoon, everybody. Well, now we are back to our seminars, and I hope everybody is fine and healthy, mentally and physically, and take care of yourself and each other. So today our guest is Professor David Kipping. He's from Columbia University, and he is one of the greatest experts on exomoons. So we have the pleasure to have you here today, David. And the talk will be on the search for exomoons. So please start your presentation.
Okay, let's see. This keeps asking me lots of permissions. Okay, hopefully you can see this.
Yeah.
Yeah, my first time using Google Meets, actually. So thanks for teaching me how to use a new platform. And thanks for the invitation. Lots of familiar faces and names I can see here. Wish I was there in person, but always a pleasure to have a chance to even virtually meet and tell you about some of the things I've been researching. And I'm going to talk today about the thing which, I spend most of my time working on, but not exclusively, and that's the search for exomoons. This has obviously been something I've been thinking about ever since my PhD. Back in 2011, I got my PhD, and I wrote my thesis about methods to look for moons. And ever since then, we've been trying to actually do this search. So what am I going to talk about today? I want to give a brief background. I'm going to go pretty quick, so please do make notes. There's going to be a lot of stuff that's on there mostly for reference. I'm not going to dwell on it too much. So if there's other techniques you want to hear about, I'm going to briefly touch on those, but not dwell on them. And then we'll talk about some the photodynamical methods we're using to look for moons, 1625 in particular as an exciting candidate, and then what's new in the pipeline, new searches. Okay, so a bit of background, and as I said, I'm going to go quickly through this bit because there's just so many methods out there. I'm splitting them into three categories. We have the transit methods, so the same way that most of the exoplanets that we now know about have been found. Gravitational and more emission, imaging, kind of more of a broad miscellaneous bucket on the end there. So the transit was, I think, the first method that was proposed to look for moons. It was by Sartoretti and Schneider back in 1999. I remember that when I was doing my PhD, my advisor used to joke that any new idea you had, John Schneider had already thought about it. He had, at the time he was prolific, thinking all different ways of detecting novel effects with transits. There was also a paper by Gila Szabo and his group in Hungary in 2006. And then I built upon this a little bit later. But the idea really is to look for the transits of the moons themselves. So if the planet transits, the moon should transit, not necessarily every time, but sometimes it will. And that causes these little extra dips in the light curve. In fact, if you look in the upper panel there, at that little bump up, that's a syzygy. So that's when all three line up, and it kind of looks like a star spot crossing. Another method that people have thought about related to transits is of course the Rossum-McLaughlin effect. It's been used for measuring spin-orbit alignments of many exoplanets. In principle, it could detect moons as well, but you need very precise spectrographs for this, sort of 10 centimeters per second. But as we're moving into ever more precise spectrographs, this might be possible. Another method related to transits is TTVs. This is almost a gravitational method, so I'm sort of splitting it between the two, but we're looking at the wobble of the planets, transit timing variations, to look for the moons. Of course, TTVs can be used to look for other planets as well. And then there's transit duration variations, which are looking at the speed of the planet to see if that's changing. When we move to gravitational methods, of course, the most obvious one here might be gravitational microlensing. And if I had to bet, I think they will probably in 10 years have the most number of exomoon detections in hand. I guess the issue with microlensing is there's a lot of degeneracy because it's very difficult to distinguish between these different, you can see these three different scenarios. They have three lenses and one source, two lenses and two sources, or one lens and three sources, and they all basically match the data perfectly. It's very, very difficult to distinguish them. And this is going to be the great challenge. So it might be more of a statistical detection, but I think exomoons from microlensing certainly have the sensitivity to do it. Another related idea, in terms of it being gravitational at least, is pulsar timing. This was, again, a very early paper, 2008, by Karen Lewis and her advisor, and they suggested that, we're using pulsar timing to detect exoplanets. There could be, or there should be, a very small residual as caused by the moons. Now, this is tiny because if you have a moon plus a planet orbiting a star, whatever type of star it is, pulsar or otherwise, then that's basically almost indistinguishable from just a slightly heavier planet orbiting the star in terms of the wobbles that it induces onto the star. But there is a very slight torque because, the planet and the moon are separated in space, and so they have a gravitational torque that they apply to the star. That torque's so small, though. I mean, it's very difficult to set, but pulsar timing could do it if the mass ratios of these moons are quite large, say 5%. Radial velocity, by analogy, is basically infeasible. So the same idea that Lewis was talking about, but if you try to apply this to looking for the wobbles of stars with radial velocity, even if you had a Jupiter-Jupiter binary, there's this paper by Murray and Correa that calculates that it's a micrometer per second residual. So it's basically off the table. I don't think we're talking about micrometer per second for a long time. And that's also true of astrometry as well, by extension. Now, radial velocity of the planet might be doable. Andrew Vandenberg's been thinking about that recently. You'd need to basically separate the light from the star and the planet and look at the wobble of the planet itself. Moving quickly on, we have emission technique. So this could be detecting the light of the planet and seeing the moon occult the planet and give it these little dips, especially if you directly image planets, that could one day work out. Eric Agol and Tiffany Jansen wrote about this idea of centroid shifts, that if the planet and the moon, the moon's moving back and forth, and so that's going to cause the center of light of the directly imaged planet to shuffle around a little bit. So that's another possible technique. And there's also just looking for the spectral separation. So you'll have some lines, if you imagine like Titan has a very methane-rich atmosphere. That methane-rich atmosphere, you might be able to detect and tell that it doesn't belong to a planetary atmosphere through a chemical model of the atmosphere, and then be able to argue that there must be a second component, in other words, a moon. And then finally, I think, or maybe penultimately, the other one I want to mention here is thermal SEDs. So if you have tidally heated moons, such as Io, that thing is hot, and so it's going to be, in fact, hotter than the planet. And so you'll get two bumps in your spectral energy distribution, so you can set the moon that way. And then radio emission has come to the fore pretty recently, thinking about the idea of detecting analogs of Io Jupiter cyclotron emission with radio telescopes. And then we have another kind of more speculative one is to look for gaps in rings. I just want to briefly mention Matt Kenworthy has been writing about this for the system J1407b. So that's all about a lot of mistakes. I probably missed some out, but the ones I'm going to focus on in what follows are just these transit methods on the left and not the RM effect. Okay, so here's our basic anatomy. We have the moon transiting first, there's the planet. Of course, the moon doesn't have to transit in first, it just is in this instance. And it causes this leading transit caused by the moon, and then the bigger, deeper planetary transit comes afterwards. So these are the type of morphologies that we're looking for. Of course, the moon itself is causing these TTVs and TDVs. And I guess the key thing I want to emphasize to you is that each of these effects are small. So the transit effect, 100 ppm, that's really pushing, and that's for an Earth-sized moon. That's really pushing the capabilities of our telescopes. The TTV effect similarly might only be a 2 sigma effect. The TDV effect maybe 1.5 sigma. So you have these, small effects. And if you really want to detect an exomoon, you really need to add them all together in a self-consistent way. That's going to maximize your chances of detection. So that's what we call a photodynamical algorithm, one that models everything self-consistently. So we've done a bunch of searches for these with this team that I put together called HEC, 100 exomoons of Kepler. This is sort of a quick overview of what we've done in the first phase of this mission, I suppose. We looked at about 60 Kepler objects of interest, as shown here. And each of these little histograms is the mass ratio of the moon to the planet. That's what you're looking at here. So every time it peaks at 0, that's pretty clearly a null detection. Or if it is pretty flat, that's clearly a null detection. A lot of CPU hours to crunch through these. And all of the purple ones are basically null. And you can see that because they tend to peak at 0. So there's no evidence for a moon there. The gray ones peak off 0. And so it looks like there's some kind of mass signal detected. However, all 11 of those are spurious. They're not moons. For instance, and that takes a lot of work to figure that out, but an example of this would be Kepler 46c, which was a false positive for us. We published it in Science, though, in 2012, even though I want to be clear, it wasn't Exomoon false positive. That's what it was. That's how we identified it. That's why we worked on it. And it turned out to be the first non-transiting planet with a unique orbit found through TTVs. That's why we ended up in Science. Another example of this, I can show it here, Kepler 138d. Again, we were very excited about this object. We thought it could be a moon. It turned out that it was just two planets interacting with each other. And in fact, we were able to measure the mass of one of the transiting planets to be 1.0 Earth masses, which at the time was the first transiting planet for which the mass had been measured at the Earth mass level. There was no other transiting planet for which the mass had actually been measured to that level of precision. So yeah, these were false positives. These were not what we were looking for, but it goes to show you that when you look very carefully through the data for exomoons, you can find some cool stuff. So from this, we kind of have this sensitivity curve that we've put together. So on the x-axis, I'm showing you the fraction of times that we achieve the sensitivity shown on the left-hand side. There's lots of ways to think about sensitivity, but here I'm talking about the mass ratio. So the mass of the moon divided by mass of the planet. As you probably know, the Earth-Moon system is about a 1% mass ratio, a little bit higher than that, 1.2. And so if you draw a line across here and then draw down when you hit this curve, you can see that we are sensitive to Earth-Moons, at least Earth-Moon mass ratios, in 1 in 8 cases, about 16%. Whereas the Pluto-Charon system, which is 10%, if it was scaled up, of course, Pluto's a little bit too small for us to detect, but if you scale that up, we will be sensitive to that kind of mass ratio quite often, about 2 out of 5 cases. So we didn't find anything, but we had these impressive upper limits. And so we started thinking about other methods once this photodynamical method ran short. Now the limitation, as I said, I mean, we did 60 planets there, 60. But there's 4,000 Kepler planets. And the reason we only did 60 is because this thing takes 2 million CPU hours just to crunch through those. It's a very computationally expensive approach. So there's a new idea, well, not a new idea, but an old idea that kind of resurfaced that was proposed originally by this Hungarian group led by Gyula Szabo and Attila Simon. And Attila Simon in particular wrote about how if you stack many, many, many transits together, shown here on the left-hand side, and they have a moon, then there's two things that you might notice. One is that the scatter in the data around the transits will be higher than it will be for the rest of the light curve, because the moon is going back and forth, and so it's kind of adding a little bit of noise effectively if you just sort of naively phase fold this light curve. The other effect that has sort of grown into a bit more prominence is, and Simon also talked about this in that paper, was that in addition to that scatter, which they call the scatter peak, there will also be a slight dimming, an average. So the average brightness will be a little bit less in the wings than for the rest of the light curve. So this is a second idea. And Rennie Heller really ran with this idea and developed it a bit more in 2014, came up with this analytical model for what the shape of these dips should look like, which is more or less what I'm showing with that white line. That's actually a numerically generated example, but it looks very similar to that. And once you have that model, you could potentially fit that to transits. Now, we tried that. We're always willing to try new ideas. We tried that and basically it didn't work. So this is our example of taking 300 planetary candidates. Now you might say, why not take all 4,000? We would have liked to have taken as many as we could, of course. We took all the planets that were greater than 0.1 AU from the star. If it was closer than 0.1 AU, we just didn't look at it. We figured it's too close to the star to have a moon. We encourage others to check that out, though, but we just didn't in this study. Of those, there's about 1,000 planets greater than 0.1 AU. And of those, about 284, after very, very careful vetting, had sort of high quality data, as we called it. So we stacked those transits together. Not only am I stacking the transits, I'm also mirroring them. So if you look at this shape in the bottom left, you can see it's symmetric, the white line. So I'm sort of mirroring it on itself just to add the signal to noise up by another factor of √2. And that black line, I'm going to show this. The black line you're looking at right here is the signal, this average moon effect signal we would expect if 100% of these planets had the exact same moon system as the Jupiter moons, the Galilean moons. So if you have that exact same moon system, that would be the effect. So that's actually inconsistent with the data. I mean, not by much, but it is slightly inconsistent with the data. You can see the data does peel down a tiny bit, but not in a significant way on the end there. The precision here is really impressive. It's 5 parts per million precision by stacking so many transits together. So unfortunately, when we do sort of the Bayesian analysis, actually the Galilean moon system is disfavored by about 2-to-1 odds. And we can even put an upper limit on how many of these planets have moons, or at least Galilean moons. And that would be less than 38% to 95% confident. So this is really pushing Kepler as hard as you can. It's very difficult to squeeze much more out than this. The only hint, as you saw, was that it kind of has a very, very slight dip over on the near to zero. And so that is somewhat suggestive of a very compact moon system around some of these. And so if you can see this kind of map here, and there's this island which I've labeled the super Io. So you can see there's moons which live at close separation as depicted by the x-axis. And they're pretty large. They're sort of in between the size of the Earth and Mars. Now, if we believe this result to be true, it would imply there's very, very modest evidence for a population of super Ios. And that kind of makes sense. The only reason why I mention this is because it kind of makes sense from a stability perspective. If any moon's going to survive inward migration, it's going to be the most close-in moons. And if we're going to detect any moons, it's going to be the versions of those which are largest. So there may be a fraction of these which do hold on to super Ios. But I have to say I'm very skeptical about that result at this time, and it's certainly not been reproduced anywhere else in the literature at this point. So, you know, the big problem as I see it with this survey and the approach so far is that what if only a fraction, you know, what if 10% of the planets have moons? Then this stacking approach just doesn't work. You're gonna lose your signal because you're reducing it by a factor of 10. So this is always the problem with stacking data. Oops. So I had a little meme I wanted to show. So yeah, the reason why, you know, people often say to me, like, why do you keep looking for exomoons? Because you've been trying. I remember actually a professor when I was on the job market said this to me, and he was like, you know what, David, you really impressed me with how stubborn you are with keep looking for these damn moons. Why don't you just do something else, like look for do spin orbit alignment measurements or do exoplanet atmospheres, because there's like a much more successful number of detections one can make doing that. And you're right, but at the same time, what keeps me going is the Copernican principle that moons must be out there. I just can't, I mean, it'd be kind of crazy to think that we are the only solar system that has satellites. They're obviously out there, and the question isn't if they exist, but how and when will we detect them? And so even these upper limits we're getting are telling us something really interesting about how satellite systems form. So we keep going. And I want to give you a summary at this point, and before we get to the more some actual candidates. So at this point, I'd say that moons within 0.1 AU, or planets within 0.1 AU, I should say, we've basically not surveyed, not spent much time on those. Planets between 0.1 and 1 AU, we can say that moons are uncommon. They're not necessarily rare. I think rare might be too strong a word to say, but they're certainly not the rule, because we're not seeing, you know, as I said, we could say that like less than a third of these planets have Galilean moon systems. So they're certainly uncommon, but not necessarily extremely rare. And that implies to me two things. It means either they, maybe I shouldn't have used the word rare here, but they somewhat uncommonly form. You know, these moons uncommonly form, don't form that often. Or they don't survive the process of where the planet forming further out and coming in. And certainly there's theoretical ideas to motivate that from scattering and from shrinking Hill spheres. And so what this tells me from an observational perspective is that this outer region, the greater than 1 AU region, is where we need to look. That is the future of this entire field. So my takeaway is that long period planets are the last hiding place for these exomoons. But you know, their intrinsic long period nature makes them very challenging because, of course, you have very few transits. So having missions like Kepler that stare at the same stars for a very long time is really what we need. So hopefully we can get tests to go for a long time, or we could use missions like HST and James Webb that can actually follow up these long period planets that Kepler had found. I mean, Kepler has long period planets, they just don't have very many transits of those long period planets. So I think there's a real idea for doing like a legacy survey with Hubble or James Webb one day. I think our approach philosophically, I'm sort of questioning it a little bit over time. We had this approach of slam dunk detection because we wanted to get everything. We wanted to see the transit timing effects, and we wanted to see the dips of the moons, and we wanted to know the radius and the mass and get an orbit. We wanted to know all that stuff. And then, you know, if all pointed at the same moon, the same type of moon, then we would believe it. And then we would write a paper and be very excited about it. Be on the front cover of Nature or whatever. But I think that approach is increasingly probably too optimistic, because truthfully, if moons are the size of the Galilean moons, and that's about it, that's as big as they ever get, then Kepler data alone just isn't going to cut it. You're just not going to get slam dunk 5-10 sigma moon detections of Galilean moons with Kepler. It's just not built to find those things. It's barely able to find an Earth-sized planet. Right, that's really the hairy edge of what Kepler can do, is to find an Earth-sized planet, even though that's what it's designed to do. But you go to a Galilean-sized moon, that's just too small for Kepler. And so the idea of slam dunk is maybe not the right way. And I think an analogy here is to think about what happened with planets. We sort of abandoned the idea of slam dunk detections for planets, quite frankly, a while ago. You know, most of the planets in that exoplanet catalog are validated planets. They're planets to 99% confidence only, which means that take 1,000 of them, 10 of them aren't actually really planets at all. So that philosophy, you know, we were uncomfortable with it when it first happened. I think many of us were like, no, I want to get a radial velocity. Excuse me, I want to get a radial velocity, I want to get astrometry, I want to get the mass. I want to know this thing's real. And now we're kind of comfortable with the idea of, hey, look at the shape of the light curve, probably a planet. And I think we're going to have to sort of build probabilistic models for understanding these observational effects from exomoons as well. So those are my takeaways. Now let's talk about Kepler 1625b and get into an interesting candidate. So as I said, I'm going fast, but please do, if you have any questions, write them down at this point, keep them in mind before I move on to the next section. I'm really happy to talk to anybody about any of this stuff so far. All right, 1625. So, and let's come back to this stacking. We had almost 300 planets stacked. This is work by Alex Tichy, who's now in Taipei as a postdoc. And from these, this was a histogram of the significance level using this out of transit average dip. So we looked at the average dip out of transit, and we just measured the sigma significance of all of these for all 300. And you can see that there's one outlier over at plus 4 sigma. So it has more than average dip by about 4 sigma. However, there is also, if you have a keen eye, one at minus 4.5 sigma. Right? You can see that. So it may just be, you know, nothing particularly interesting about this. So when we saw this, we were, you know, I have to admit, I was pretty skeptical that this was anything significant. And it also corresponded to a very large moon. The size of the moon required would have been about 4 times that of the Earth. And so we jokingly called it a Neptune in the group for a long time because it's like a Neptune-sized moon. But it was interesting. And the reason why I think we pushed harder on it was A, it's because it was the best we had after looking through all of this data. And B, the object, am I going to put an arrow on it? There it is. It's that guy. So all those colored circles are the planets that we looked at. Their period and their radius, like a classic Kepler plot here. And this is that planet. So it is basically the best planet a priori for having a moon in our sample. It is a long period 1AU Jupiter-sized planet on a circular orbit. We can get its circularity from the shape of the light curve. And it has one of the highest signal to noises we would expect. This is sort of assuming it has a certain size moon. I think in these cases we assume the largest moon it could dynamically hold on to. What would be the signal to noise of that transit? And you can see it is basically the highest. So everything about this target is even a priori the best, and it has a hint a posteriori of having a moon. So we didn't feel this was compelling to write a paper and claim we found a moon, but we did think it was a good excuse to use Hubble or ask for Hubble time. And Hubble agreed, the TAC agreed, and gave us some telescope time to look at it, chase it up. And then we got the data. And Obviously, there's a lot of systematics with Hubble data you have to deal with. There's this sort of breathing effect. There's hooks caused by sort of charge trapping. But when you remove those effects, there's basically only one effect left, and that's the one you can sort of see on the left-hand side, the left panel. This is actually, every single panel here is the same transit. We only observe one transit. This is just 6 different ways of looking at that same transit. The data on the left is identical in those 3 panels, but I'm just showing you 3 different ways of correcting the only remaining systematic, which is this so-called long-term visit long trend, which is very, very common, seen very often in long stare observations photometrically with a wireful chemistry instrument. So the most common approach for this is to use a linear trend. It's like most papers use a linear trend in the atmosphere community for doing this. So that's the top left. And if you use that correction, you can see on the right-hand side what you get. There's something pretty interesting going on. If you try a quadratic trend, you basically get the same thing. And you try even a model that nobody had ever tried before, but we thought, hey, why not give it a go? We tried an exponential trend, sort of motivated by sort of a charge trapping hypothesis. And again, we see the same thing. It has to be said that no one really understands what causes this trend yet. There's no well understood, agreed upon consensus of what the physical origin of this effect is. But you can correct it with these heuristic models. In each case, the evidence for a moon is pretty strong. Doesn't really matter how you detrend this. You do see evidence for that dip. And the other thing I want to point out, there's basically 2 anomalies here. There's the dip, of course, which occurs 3.5 hours after the primary transit. But there's something else. There's the TTV, and you can actually see that on those 2 vertical lines. The dashed line is actually where we would expect the planet to transit. So if you take the Kepler ephemeris and you extrapolate it forward, which obviously we did for the proposal, it should transit on that dashed line. But you can see the mid-transit point comes in early on the solid line. In fact, it comes in about 78 minutes too early, almost over an hour, which is a lot. And this is a very precise telescope. So I think it's hard to argue that's a systematic somehow. In fact, if you look at the TTVs and just lay them out, that 7th epoch, which is the HST transit, the last one, you can see how early it comes in. Now, what's particularly interesting is that if the moon comes in late, which if that dip is a moon, then it clearly has come in late, it's come in after, then the barycenter lives between the planet and the moon. So that means the planet would have to come in early. Okay, so if the moon comes in late, the planet has to come in early, and vice versa. And that phase relationship is true here. So that's another assuring sign. So, we did a lot of tests on this. It's very difficult with one convincing transit to do much with this. Certainly when we do the photodynamical modeling, we can explain this quite naturally. Both the radius corresponds to a Neptune radius, and the mass that's required is a Neptune mass. So both the mass and radius of these 2 independent effects agree with the same type of moon. The semi-major axis of this moon would be about 40 planetary radii, which is well within the Hill sphere of the planet. And in fact, this system is remarkably eerily similar to sort of the Earth-Moon system, but scaled up. If you basically blow up the Earth-Moon system by a factor of 11.4, as depicted here, you pretty much get this system. Now, I'm not claiming by any means this formed by the same way the Earth-Moon system did, but it's kind of an easy way to remember the properties of this system. It's a 1% mass ratio moon system. It's about a 25% radius ratio, and it has roughly the same sort of planetary radii separation. And it lives at 1 AU, the same as the Earth. So it has many easy to remember properties by thinking about the Earth-Moon system. An interesting prediction from our model, because this is a photodynamical model, we can actually predict what the planetary mass should be. And we predict the mass would have to be certainly greater than Jupiter, and in the range of sort of 2 to 3 Jupiter radii. The most likely is about 3 Jupiter radii, sorry, 3 Jupiter masses. And so that's something we could test by getting radial velocity measurements of. Finally, the other thing that was concerning when we looked at this analysis originally is that the Kepler DR24, data release 24, said that this star was 0.8 solar radii. And there's basically no way we can fit this with an exomoon model if that's the true radius, because it changes the density of the star a lot, and that makes the planet have to be highly eccentric, and the moon becomes unstable. So the moon hypothesis is wrong if the stellar radius is 0.8, but DR25 revised it by almost a factor of 2.5 here to 1.8 solar radii. So like, what happened between there? So obviously you'd think, well, that's a pretty big change, and we can only explain it if DR25 is right. From DR1 to DR24, it was 0.8. It's only DR25 it moved up. So spectroscopy could test that. These are things to keep in mind. The host star is faint. It's 14th magnitude, pretty faint by Hubble standards, atmospheric characterization standards. And so the transit is long, 24 hours. And so follow-up is really challenging. You're not going to follow this up from the ground. You can't do a 24-hour transit from the ground. It's just impossible unless you have like an Antarctica telescope or something. So it's really basically impossible to follow this thing up from the ground. Space-based telescopes are obviously very difficult to get time on, and we've not been able to pursue this any further since. Could it be a false positive? Well, this is sort of a time series of where this, we'll go through these pretty quick. Here's a time series of the South Atlantic anomalies, as they're called, when Hubble goes through these regions and the Van Allen belts of the Earth. And basically, the moonlight region is way, way outside. In fact, it's kind of amazing. The phase 2 primary support contact told us that he's, if you read that last sentence, he's still shaking my head about how well this worked out. We had so few, we had like an anomalously few number of South Atlantic anomaly crossings. It's, yeah, he says here, to say that you lucked out with how well this interacts with SAA is an understatement. So we have one of the most pristine like Hubble time series you could ask for in terms of being corrupted by that effect. So that makes me think this is unlikely. Could it be something to do with the centroids, like the star shifted position or the telescope shifted position? We have very, very stable centroid pointing again, and it's actually most stable where the moon dip occurs. You can see it's highlighted by those vertical bars. It's the X and the Y positions. And we also don't see any correlation between flux and centroid position. So I don't think this is happening. The signal appears achromatic. If we split our light up into blue and red, we see the dip in both wavelengths. So it doesn't appear to be like a star spot effect or anything like this. We don't think it's a planetary interloper, another transiting planet. We could have accidentally set another transiting planet, but really Kepler should have seen it. If there was a Neptune-sized planet in the system, how did Kepler miss it? And that puts a lot of pressure on this. In fact, we calculate the probability is significantly less than 1%, I think like less than 0.1%. Finally, the star is quiet anyway. It doesn't have any, we can't even detect a rotation period for this thing. It's so quiet. The ppm scatter is like less than sort of 100, 150 ppm from the Kepler data. So this is actually an unusually quiet star. So it would be odd for it to create a 500 ppm moon dip. Another author, René Heller, who I mentioned earlier, he actually has an alternative suggestion for what could be causing this. He said, well, maybe the TTVs are being caused by an unseen, non-transiting hot Jupiter in the system. That could possibly do it. So if the hot Jupiter is really, really close to the planet, close to the star, but it's tilted over so it doesn't transit, then it will wobble the star back and forth, and that could be the TTV that we're picking up. Now, I think the reason why he put the Jupiter, why he didn't do like a resonance system, is because if you put the Jupiter close, it's going to be undersampled. It will create an aliased moon-like TTV. It's very difficult to create a high-frequency moon-like TTV, but a hot Jupiter could do it. Of course, such a hot Jupiter would also be detectable by RVs, giving signals here of like 900 to 150 meters per second. So again, another good reason why we should follow this up with RVs. Laura Kryberg and her colleagues independently went after this. They, like René Heller, independently recovered the TTV signal. Heller does see the moon dip, but Kryberg does not. So that's two of us that see the moon dip, one who doesn't. And I guess, well, the moon dip's kind of there, but it's significantly attenuated, as you can see here. So that's obviously concerning. We've been in a lot of contact with them trying to figure out what on earth happened between the two differences. And frankly, we're still scratching our heads about how these, two analyses could arrive at it and one doesn't. It's very confusing. However, one thing we noted in a follow-up paper, and I'll just mention here that maybe has something to do with this, is that if you look at the two reductions, this is the raw photometric reduction we get from the two pipelines before we do any linear trend long-term corrections. There is this much larger offset in their data, as you can see here, which occurs during the visit change. So that's basically when Hubble has to sort of reacquire the star. Now, we think Hubble reacquired the star, and that's, we're fitting the centroid positions pretty much perfectly. It's almost back right on it. Whereas in the analysis of Kepler, they get a larger centroid shift, and they get a significant change in the flux between those 2 points. That's obviously quite a way out from the moon region, but it's kind of concerning. The other thing that's really odd, if you look at the RMS of each orbit, so there's actually 26 Hubble orbits used for this observations. On that let's see, is it the 22nd? Yeah, the 22nd orbit. You can see that our scatter, which is the gray point, all the gray points are the scatter from our analysis, is pretty consistent with the scatter we got for the other orbits. But for the other analysis, they get a really low, it's like less than 100 ppm, which is really surprising compared to the rest of the data. If that's 85 ppm, and that's a 1 in 16,000 event. So it's possible that happens by chance, and you can see it there, and that's right in the moon region. So for some reason, that orbit has really, really low photometric scatter. I don't understand that at all. It really shouldn't happen unless you're extremely lucky, and we obviously don't see it in our analysis of the same raw data. So I do not understand what's happening on that orbit, but it seems to be maybe something to be concerned about. And then finally, when you look at the centroids, another thing I already mentioned is the star is pretty stable in the centroids, but in the Kreiberg analysis, they do see much larger centroid motion than we do. And as I'm sort of depicting here between these two panels, so you can see whenever you have red, that's their analysis, gray is ours. And all of these numbers, the inter-orbit range, the intra-orbit range, all of them are inflated by like a factor of 2 between the two analyses. So that's really strange. Like why is it that the star is moving around twice as much in their reduction than our reduction? I really don't understand that. So we're basically stuck, and I do think maybe another reanalysis might help at this point, or just really frankly reobserving the thing. So some concerns. Egress has not been clearly observed. You can see it basically ends right when our observations end. So that's one of my biggest issues with this personally, is that I would like to see a nice flat baseline afterwards to really believe this is 100% slam dunk. And of course, the other thing is that the signal is dominated by one transit. So I'd want to see this repeat to be, a confirmed exomoon. And of course, there's no precedent. I mean, this is a Neptune-sized moon. And that's immediately worrying. Of course, theorists have no problem explaining anything. I mean, you can give them Boyagin star, you can give them, the random transit, this Neptune-sized moon, whatever it is, theorists always have a way to explain it after the fact, but it really wasn't predicted. So, and there's nothing obviously in the solar system like this. That's somewhat concerning. Yeah, I've already mentioned that. There are these papers I point you to if you want to read about the formation mechanisms that have been proposed for such a large moon. Unfortunately, we were not able to secure follow-up time. We did ask, and this was our prediction. So for the next epoch, epoch 9, we were predicting this. So this is the forward prediction of our models. We predicted there was a 62% chance the moon would transit in that epoch. And if it did, you can see the vast majority of our models predict it should have happened early. So this would have been pretty nice, because we could have gone after this transit, and if this thing shows another blip, it really should occur in that region. And if it does, then we pretty much, I think, have a nice slam dunk case that this moon is real. If we don't see a blip there, it does start to put pressure on the moon hypothesis. And I think at that point, I maybe be comfortable not giving it any more time. But I think it's a shame that we didn't get the time to chase it up. Now, if you go forward in time, so the next epoch, you can see what happens. Uncertainty grows. And so now we basically can't predict for any of the future transits where this moon will be. It could happen before, it could happen afterwards, and it's basically equal odds. So you have to basically reacquire phase on this object. And that's not going to be particularly compelling now, because if I say, look, we foresaw a dip and it happened before transit, but I have no predictive ability to tell you I was expecting that to happen, it's not particularly convincing. So there's a few things I mentioned here that we could test besides from Hubble. Hubble would be great, but we don't have Hubble, so what else can we do? There's RVs and spectroscopy, as I've highlighted here. So there is some work that's in prep by Andrew Howard that's been trying to obtain the radial velocities of this system. And he sees very clearly the evidence for this planet, which is perhaps not surprising. The planet was already validated, so we already thought this was a real planet. The mass of this thing comes out to about what we would expect. I'd also mentioned very briefly before that the spectroscopy shows that this is almost certainly not this 0.8 radius thing. Everything about it suggests it really is slightly evolved, and it's closer to the 1.8 solar radii. So we have actually a very precise, within a few percent, radii measurement based from isochrone modeling now. So that relieves one concern. The mass from this comes out to be 2.3, which is pretty, and this is preliminary. This might, I have to advertise, this will certainly edit a little bit as new, because this is still under observation. So new data is still coming in. But preliminary, it's 2.3 Jupiter masses, which is fully consistent with our prediction. We said it really had to be greater than Jupiter mass. So that's nice that this is coming out. And remember at this point that TTVs could be caused by an unseen non-transiting hot Jupiter that was suggested by another author. And we think that's basically excluded because we don't see any evidence in these RVs for another short period planet. In fact, if it would have to live somewhere on that black line to explain the TTVs, and you can see our upper limits from the RVs put a lot of pressure on that. So I think this is the idea of a hot Jupiter that's tricking us is pretty much excluded by the radial velocity data at this point. But stay tuned because this is all work that we're still collecting data for. So some takeaways. TTVs are agreed upon by all parties. So we know these TTVs are real. We also know there's no other transiting planets in the system. And we know the RVs do not detect any other planets in the system, including putative hot Jupiters. And it's indeed starting to put pressure on resonant systems as well, resonant configurations. So the system appears empty despite the fact the planet wobbles. So something's wobbling at 1625. It's either something hiding deep in a resonance, causing a lot of wobble that's pretty small, or it really could be the moon. The moonlight dip is seen by 2 out of 3 teams, and this is obviously a big concern, the fact that the third team was not able to reproduce it. However, I do think there's some strange features in that third reduction, and it's unclear what is causing this difference, which is, essentially a 5 sigma effect. It's kind of odd that we can't agree on a 5 sigma effect. So either we need more reductions of this or follow-ups, but I do think that having analogs, as sort of illustrated by this meme, would also help, because if you just think about the story of hot Jupiters, the first hot Jupiter was met with a lot of disbelief by the astronomical community at the time, because there's no precedent for a hot Jupiter. But once you found 10 of the things, I think we became more comfortable with the idea that hot Jupiters were real. And so, the first Neptune-sized moon is obviously going to be a point of concern. If we never see any of the Neptune-sized moons ever again, 1625 is probably not real. But if we keep detecting a bunch of these things with future missions, then it actually lends, I think, more credence that this is a priori a physical output of these systems in some cases. Doesn't mean they're very common. Hot Jupiters aren't very common, but they dominated early detections. Point 3, the moon model successfully explains the photometry with a self-consistent solution. The mass, the radius, all this would be nice, but still more tests would be great. Maybe I'll mention another test in a moment if I have time. And that's basically where we're at with 1625. So I think the key point now is a nice segue is if you want to find more analogs, then go out and find them. So do some more searches. So let me tell you about new search ideas and strategies in the last sort of 10 minutes I have. So I think it's easy to conclude from the data that, the Kepler data, that there are very few moons out there. I think you would be forgiven to draw that conclusion, but I don't think it's the right conclusion to draw, because one of the main observational consequences of exomoons would be TTVs. In fact, that's the easiest thing they produce. The most detectable thing they do is to create a TTV. It's easier to set than the dip. And when you look at the Kepler data, this is 2,400 Kepler planets that exhibit TTVs, as listed in the Holsker and Mazet catalog from 2013. Like, there's a lot of systems with TTVs. They're very, very common. You know, some of them are very, very small amplitude, but they are statistically significant. There's a lot of TTV systems. And what's kind of crazy is that hardly any of these are inconsistent with being a moon. So we wrote this paper called Impossible Moons, and we find that of these, only 179 of them are absolutely impossible to be a moon. And that's basically because the amplitude is so big that it would require the moon to live outside the heliosphere. Even if it was like the binary planet, the mass ratio of 1 is sort of the physical limit of the mass ratio, these things would have to live outside the heliosphere to create the TTV effect. So that doesn't mean the remainder are moons, but they are actually consistent with moons. It's just that we can't tell the difference. Hardly any of these have really unique solutions for. And so the real problem with TTVs, as I see it, is they have been traditionally thought of as ambiguous. In most, it could be a planet-planet system. That tends to be what we assume, but it could be a planet-moon system. And this reminds me a lot of the early days of planet hunting, because we had the same thing. You know, a transit by itself wasn't enough to claim a planet, because it could be a star with a planet, but it could also be a star with another star, like an eclipsing binary, a hierarchical triple. And the way we eventually solved that, as I've already sort of alluded to, is this validation technique. You know, that Willy Torres pioneered, Francois Frezin with Blender, and now we have Vesper from Tim Morton. These validation techniques have changed the game because they really think of these systems in a statistical sense. They look at the light curve shape and they assign probabilities to these different scenarios. And so to me, I think that is the future of planet-moon hunting. Unless we get just far, far better precision, we can do slam dunks. Without slam dunks, we're going to have to think about statistical ways to validate moon signals. And at first that seems jarring, but I think it might be, we might become more comfortable with it, as we did do with planet validation over time. So some ways of doing this that I'll briefly highlight is, one is this exomoon corridor effect, which I read a paper about very recently, just this year. And the idea is that if you're I'm just going to skip through this to be quicker. If you look at an exomoon signal, think about the Earth-Moon system. The moon goes around the Earth once every 27 days. The Earth goes around the sun once every 365 days. So the moon has done 13 revolutions each epoch of the planet. So an alien watching the Earth, that signal, which is the gray line, is much, much faster than your sampling rate. So you have an undersampled signal. And so if you actually sample that at each epoch, at the integer number of epochs, which are the black points, then the signal you think you see is the red line. But that is not the period of the moon, right? That is not the frequency of the moon. That is the frequency of the alias of the moon. The true moon frequency is much, much higher. You just can't sample it. The well-known effect, you know, we see this all the time. Think about looking at a car wheel spinning as you drive down the highway. You know, it has this kind of stroboscopic effect as it sort of seems to spin backwards and then still. And it's really the same effect here. So exomoons will always cause undersampled. There's no option just from dynamical stability. They have to cause undersampled TTVs. And at first that seems annoying, but you can actually figure out an equation that relates the period of the moon, the period of the satellite, to this the expected TTV frequency. And then you can play some interesting experiments. So what if we created an artificial moon population and we asked ourselves, what does the corresponding TTV period population look like? So here's my fake moons. I'm going to, just for fun, let's assume they're uniformly distributed in 1 over the satellite period. So we have a pileup of short period moons. That's basically what I'm doing. That's the moon 7 major axis. That's the frequencies that we would get for the TTVs. Pretty uniform, and that would be the period of these TTVs. It kind of almost looks like an exponential. And what's interesting is that 50% of these moons have periods, TTV periods, less than 4 cycles. So the minimum is 2, and the 50th percentile is 4. You can't have a cycle less than 2, otherwise it's an alias again. So between 2 and 4 cycles, half of all moons live there. Now you might say, okay, David, you just assumed a very specific distribution there, uniform in 1 over PS. Try something else. Fine. Okay, let's try uniform in log 7 major axis. Oh, what a surprise, we get the same thing. Let's try uniform in semi-major axis or proportional to semi-major axis. It doesn't matter. Whatever you assume for the moon distribution, as long as it's not pathological, you use like a delta function or something, as long as you have a smooth distribution, it always produces this result where half of the moons give TTV frequencies between 2 and 4 cycles. And that's really a result of the undersampling itself. Now, what's interesting about that is that very, very few planet-planet interactions do that. In fact, of the systems where we know about planet-planet TTVs, and we've been able to figure out the system, Sam Haddon had a great paper where he looked at about 130 such Kepler systems. You look at their TTV periods, they're typically quite long, and less than about 1% of them have TTVs in this so-called exomoon corridor between 2 and 4 cycles. So if you see a short period TTV, it's kind of interesting from a moon perspective straight off the bat. Now, I wouldn't say a priori it means it's an exomoon because it depends on the prior ratio of how many perturbing planets there are versus perturbing moons, but it's immediately very interesting. So we wrote this paper, I wrote this paper just this year highlighting this effect. Now, the caveat is that there are selection effects in that orange histogram there. This is Haddon-Lithwick's sample, and they're just taking everything where it's possible to derive a solution. And so there's definitely a selection effect there, and clearly more work needs to be done to sort of figure out whether there is a sample of short period TTVs that maybe Haddon is just missing in this sample. Yeah, we're working on some code to sort of develop this a little bit further, but for the sake of time, I think I'm going to skip through this. We are working on a new candidate found through this method. It's a long period Saturn. It shows a nice high frequency TTV. It's about 6 minutes. It would correspond to about a half Earth mass moon if it was real. We, again, were sadly turned down for Hubble time, so we can't follow it up. But, maybe we'll keep trying. We're going to try and analyze the data we have as best we can. But this is another really compelling signal because it's very, very difficult for planet-planet interactions to do this, and there's no indication of anything else in the system. And our preliminary RVs indeed show there's nothing else in this system. So again, a really compelling exomoon candidate potentially. I think the final thing I'll say, because I'm running out of time, is there's this other method that you will see in the archive in the next couple of weeks on transit folding. And what I want to say, I mentioned this point that when the moon comes in late, the planet comes in early. And so really you could use that. If you knew there was a TTV of a planet, you could predict where the satellite should be, modulo the mass ratio. That's really the only thing that matters. The smaller the mass ratio, the further out the satellite will be. The higher the mass ratio, the closer in, because it's just the law of pivots, mass times by separation. And so if you guess the mass ratio, just guess it's 2%, then you could predict precisely where that moon would have to be in order to cause the TTVs, and you could stack. So you could try, don't just guess one mass ratio, guess many, and you could do a 1D grid search, which I'm showing you here. So we're doing a grid search from a small mass ratio up, and we're stacking that region where we would expect the moon to be to cause the TTV. And you can see in the bottom, you're able to reconstruct the moon signal. So this is basically like a transit fold, but for moons. It's a folding algorithm for exomoon signals. If you do a conventional fold, just fold on the period blindly, the normal fold that we normally do, you can't see the exomoon in there at all, as you can see at the top. But using this new algorithm, which just has one, so it's very, very fast, it's just one parameter to search through, you can very quickly look at a TTV system and see if there's any evidence for a coherent moon dip, which could be causing it. So I'm really excited about that. No photodynamical modeling is involved. It's very, very fast. Look out for the archive soon where that will be coming out. It's just been, got a very good report from MNRAS, so it should be coming out pretty soon. Okay, so I think I'm going to stop there because I know I'm low on time. These are just some bullet point things. If anyone wants to ask a question about any of these, just to remind you the things I've covered, and would love to take any questions you have. Thank you.
Thank you, David. Fantastic presentation. Great. And really hot topic. So now we are open for questions. Anybody would like to make a comment or a question?
I have a question.
Okay, Ricardo.
Well, David, thank you for the talk. Very good. You talk about the wobbling of Kepler 1625 being caused by the moon, and the moon being a Neptune-sized body. Could this wobbling is being caused by more than one moon, like two smaller moons, instead of just one big moon?
Yeah. Possibly. We didn't test 2 or 3 moon models in our analysis. The problem with adding multiple moons is that in general you would diminish the TTV. So if you add, unless they're resonant, if they're non-resonant moons, then in general the TTVs wash each other out. They cancel each other out, and so the net effect would be that if you're making the observed TTV smaller, but you have a significant TTV detected, it would require the mass of the moons to be bigger to explain that same TTV. Unless they're resonant. If they're resonant, they co-add.
Yeah, but I was thinking exactly about resonant moons because the system's so extreme, and if you imagine like 2 Earth instead of 1 Neptune, they should be in a resonance, I think, just for them to be stable. Maybe if you have more moons and the moons are like Earth-like moons, they will not be stable if it's not in resonance.
Yeah, I mean, you could certainly have, you could like put in, I don't know, 4 or 5 Laplace resonant moons or something, and you could, I'm sure, I mean, there's no, whether you could fit the TTVs with that model is not really, there's no doubt about that, because you'd have 5 moons, just hypothetically, 5 moons, and each of them would have 7 orbital parameters. So you'd now have, you know, dozens of free parameters to fit 4 data points. So there's no question you could explain the TTVs with more elaborate models. I don't think there's any question about that. You wouldn't be able to explain the dip though. You'd have to basically run the dip off as, you know, as systematic or something, and just pretend that's not there. Because the dip suggests there is a large object close to the planet that is of order of Neptune size. So you'd have to have, if you believe that dip, then you'd have to have at least a Neptune-sized moon in there, plus something else in resonance. And you don't need that to explain the TTVs, right? You can explain the TTVs just sufficiently well with one. So I'm not sure there'd be a good motivation for it, but you're right that you could almost certainly fit it. I just don't know it would prove much, but I believe that you could fit it with multiple moons.
Okay, yeah, thank you for the answer. I was just asking from a dynamical point of view. I have no idea how the TTV will work in this case.
Okay, thanks, Ricardo. Anybody else? Well, I have one question. Is a little bit, let's say, not directly what you were saying, but you presented your concerns about this 1625b and not being predicted such large moon.
Mm.
So what are your feelings about how should be or could be the origin of this body? Would be reasonable to think about the real formation in locus or something like that?
Yeah, so there's a couple of papers on the formation. One of them suggests that the planet could have had a very massive disk. That's pretty strange because we don't see, I mean, we don't really have observations of circumplanetary disks, to be honest with you, but most models assume that the disks are somewhat comparable to the disks that form the Galilean moons and Saturn's moon. But that's also, of course, problematic because we're basically tuning all of the models to the solar system. And we know from exoplanets that has been not a good idea in the past. So I'm a little bit cautious about that. But I think the size of the disk that would be necessary is certainly pretty extreme. And then there's also this pull down capture mechanism that Brad Hansen wrote about. And that has the nice property that, so this is basically, there's basically kind of like a co-forming planet nearby, essentially. And the two get bound together, get pulled down together during the formation of the giant planet. So this is nice because it pushes the moon very often into an inclined state. And we do have some evidence that this moon would need to be inclined. our favored inclination is about 45 degrees from the first dynamical modeling. It's like 45 degrees plus or minus 25 degrees or something. So it's like a giant error bar. But
yes, it's a large inclination, yeah.
Yeah, so the pull down, I guess capture mechanisms in general have no issue producing inclined states. But I'm not a theory. I don't work in the theory side. But
I know, yeah.
Yeah.
Mainly the idea. I was thinking about if you have a pair forming a orbital pair, because you find that when you are studying planetary formation, you may find it's not difficult to find the orbital pairs being formed.
Right.
So
right.
Nearly orbitals. So perhaps that could be a kind of origin too, but it's just a guess. I think it has to be simulated to see how feasible it is.
Mm-hmm.
Okay, good. So we are open. Anybody else? Any further comment or question? Okay, so I think that's it. Thanks very much for presentation. I think it was a great presentation. Certainly some of us are going to watch it again to get some points. It was very intense, I would say, a lot of works, and you present a kind of review with an update to the present state. So thanks very much.
My pleasure.
Okay, and let's hope we meet in person at some time.
Yeah, that'd be great.
Okay, good.
Thanks,
good.
everyone.
So